Hi everyone, welcome to this week's live stream. So this week we are going to be doing Lewis structures, and we are going to be working on, first we're going to do some simple Lewis structures with neutral molecules, and then we're going to do some work with the polyatomic ions. And just depending on how much time we have, then we may go back and determine if these molecules are polar or nonpolar based on their shape. But I'm not sure if we'll be able to get to that or not. I really want to make sure that we get through all the Lewis structures that we have. Okay, so let's go ahead and get started. Okay, so on each slide here, I am going to have the rules for Lewis structures, just so that they're always there and we can always refer back to them. Now, these are the rules that I like to use that help me the most. You may find that you like to modify rules just a little bit, and I'll show you how different people think about doing Lewis structures in different ways. Now, before we start, I do want to say make sure you have a periodic table handy. So I keep one over on my wall here, but you're going to need to be able to know how many valence electrons each atom has. And to do that, it's really handy to have a periodic table just right there, because it's really easy to determine the valence electrons then. With that being said, let's go ahead and start our first Lewis structure. All right, so we're going to be doing CH4, otherwise known as methane. And you can see my first step here in my rules for Lewis structures is I add up all of the valence electrons. So I think about gathering all of the valence electrons and basically putting them in one pot. And to do that, I have to see how many valence electrons each atom gives me. Okay, so let's switch over here. So carbon, again, check your periodic table. If you find carbon on the periodic table, you will see that carbon gives you 4 valence electrons. There's only one carbon here, so it's just 4. Next, we need to do hydrogen. Now, there are 4 hydrogens, so I'm going to have a multiplier of 4 in front of hydrogen. Again, finding hydrogen on the periodic table, you can see it only has 1 valence electron. So there'll be a 1 there. I just add this together and I have 8 total valence electrons. Okay, let me just make sure that there are no questions here. Oh, I've got a comment that my volume is kind of low, so let me fix that. See if I can bump that up just a little bit. So hopefully this is a little bit better without being too much. Okay, back to our Lewis structure. So we have our total valence electrons. Of course, we got this from mostly the periodic table. And now we need to make a sketch, make our best guess as to how we think these atoms are going to be arranged. Now, there's a hint that I like to use, and that is often the first atom that's written is the central atom. This is not always true, but it is usually true. So if I'm looking for methane, I see that my carbon is written first. So I am going to assume that that is my central atom. I'm going to make that my best guess and see if I can come up with an arrangement that I think might work. So I'm going to put carbon in the center and my 4 hydrogens around. Now, what you might find is that your first best guess actually is not the correct guess. Well, that's fine. You can always go back and start again. That's completely normal. A lot of Lewis structure, I feel like, especially when you're first learning it, is you guess and test. You try something, you use your tips and your tricks and your hints, and then always be ready to try something else. Sometimes we can get really focused on always doing it one way, and that's when it can get really frustrating. Okay, so here is my arrangement of atoms that I think is my best guess. Now I am on my third rule for Lewis structures, and I'm going to start sharing electrons between atoms. Now, to form a bond, I need to share at least one pair or two electrons. So that is what I'm going to start with. You know, I think I'm going to put my electrons in a different color. Okay, so let's put 2 electrons between this carbon and this hydrogen. And then let's put 2 electrons again between carbon and this hydrogen on the right. And 2 electrons here and 2 electrons here. And now I have at least formed a, let me move that out of the way, formed a bond between the carbon and all of the hydrogens. And it looks like maybe I need to bring my volume up just a little bit more. So give me just a second. I will adjust that. And hopefully this is a little bit better. I can also adjust in here a bit. I don't want to blast y'all out. I know sometimes it gets a little bit staticky. Okay, so now I'm going to see how many electrons have I used at this point. Well, I've used 2, 4, 6, 8. I have used all of my valence electrons. Okay, so now I want to check and make sure that all octets are satisfied. Now, one thing to remember here is for hydrogen and also for helium, although you don't see helium very often, they only need 2 electrons actually to have the octet satisfied. That gives hydrogen a full outer shell. Remember, hydrogen only has the 1s orbital and it can only hold 2 electrons. Okay, so I'm going to draw some, let's maybe go yellow, some circles around here. So that hydrogen has a full outer shell. So I would say its octet is satisfied, even though, again, it doesn't have 8 electrons. The same with each of these hydrogens. They have a full outer shell. They each have 2 valence electrons, or sorry, 2 electrons. Now, if I look at this carbon, it should actually have 8. It should have an octet, and you can see I have 2, 4, 6, 8. So I have also satisfied the octet for the carbon. So all octets are satisfied. This is a valid Lewis structure, and it is a Lewis structure with single bonds between the carbon and all the hydrogens. Now, one thing I will do is I will write this a different way that might be a little more clear. So instead of doing the electron dots, I'm going to draw bonds. And you have probably seen the structure for methane at some point, even if you didn't know what a Lewis structure is. So hopefully this looks correct and this looks right for you. Okay, this is the Lewis structure for methane. Let's go on to one, well, we're going to increase difficulty by increments, but let's go to our next structure. Okay, so our next Lewis structure is going to be NH3. This is also known as ammonia. We are going to follow the same set of rules. I'm just going to keep them up again for all of the problems. So my first step is to add up all the valence electrons. So nitrogen, I only have one of these nitrogens. Again, if you find nitrogen on the periodic table, you will see that it has 5 valence electrons. Now I need to add in the hydrogens. I have 3 of them, so I'm going to have a multiplier of 3. And of course, each hydrogen, just like with methane, gives me 1 valence electron. And you can see that this structure also has 8 total valence electrons. Okay, that is my first step done. Second step, again, I'm going to take my best guess as to the arrangement of these atoms. Because nitrogen is written first, I'm going to put it in the middle, and I'm going to put each of the hydrogens around the outside, just like I did with methane. So here is my nitrogen, and I'm just going to put these hydrogens out here. And they can go wherever. You could have put a hydrogen up above the nitrogen. That's totally fine. It does not make a difference. Especially at this point, it does not make a difference. We just want to make sure that we have satisfied everybody's octet at the end. So now that I have my sketch, I have my first best guess. I'm going on to step 3 of my rules for Lewis structures, and we're going to make Make sure that my atoms are sharing at least 2 electrons because I'm going to form a bond. So let's put those electrons in. Again, I'll use a different color. So a single bond between nitrogen and that hydrogen, same here. Same here. Okay, so at this point, I have a bond between the nitrogen and all 3 hydrogens. So let's see how many electrons I've used. I've used 2, 4, 6 electrons, but of course I have 8 total electrons. So I can't just stop at 6. I need to make sure that I use all of my valence electrons. So I'm going to put a lone pair, or sometimes called a non-bonding pair, on nitrogen right here. Now I have used 2, 4, 6, 8 valence electrons. And so I have used all of my valence electrons. You cannot create electrons and you cannot destroy electrons. Now let's see if I've satisfied the octet for all of my atoms. Okay, so this hydrogen has 2 electrons. It's fine. The same with this hydrogen and this hydrogen. Now I need to check my nitrogen. Here are all the electrons around my nitrogen, and you can see I have 2, 4, 6, 8 electrons. So nitrogen also has an octet that is satisfied. This means that I have drawn a valid Lewis structure. I've used all of my valence electrons. All octets are satisfied. And let me just draw this with the bonds like I did for methane. So nitrogen has a single bond to each hydrogen and a lone pair, or again, a non-bonding pair as well. Okay, before I move on, let me see if there are any questions. Okay, it doesn't look like there are any questions. These hopefully are pretty easy structures. Again, I like to start with the easier ones so you get comfortable with the rules and we can build confidence as we go. All right, so we have a very famous molecule here. We have water. Let's draw the Lewis structure for water. Again, we're going to follow the same rules here, even though you probably already know the Lewis structure for water or you have seen it. Let's go through our rules. Let's go through the steps, and you can see how we arrive at what the water molecule actually looks like. So valence electrons. In this case, hydrogen is written first, and I have 2 of them. So I have 2 hydrogens. Each one gives me 1 valence electron. Plus oxygen is going to give me 6 valence electrons. There are a lot of structures that have 8 valence electrons. So again, we have 8 total valence electrons. Okay, on to my step 2 here. I'm going to sketch out the atoms. Now in this case, hydrogen is not the central atom. So usually the central atom is written first, but again, this is a situation where it is not written first. It would be unusual to have hydrogen as a central atom because it can only form 1 bond. It can form a linear molecule, and that maybe wouldn't have a central atom. So I'm going to put oxygen as my central atom. So here is oxygen in the middle, and I am going to throw these hydrogens just around it, wherever. Again, it doesn't matter if you put them on the left or the right or above or below the oxygen. They just need to be somewhere around there so we can put electrons in. And now let's make single bonds. Let's put 1 pair or 2 electrons in between my atoms. So we'll make a single bond between oxygen and this hydrogen, and a single bond between oxygen and that hydrogen. Now, what I did with ammonia was I went back and saw that I had 8 valence electrons, and like here I've only used 4, so I put the other 2 in. But another way to think about this is to already think about, have you satisfied octets? So you can see this hydrogen and my second hydrogen, the octet is satisfied, but for sure oxygen only has 4 electrons around it right now, and it needs 8. So we have not satisfied the octet for oxygen. So hopefully what this tells you to do is to go back and use the rest of these 8 valence electrons. So I have 4 more electrons. So I'm going to give oxygen 2 lone pairs, or again, some people call these non-bonding pairs. And I have used 2, 4, 6, 8 electrons. Again, that's how many I need to use. I can't just throw electrons away or create them out of thin air. And now if you see, again, the yellow or gold circles that I've made, again, the hydrogens have stayed the same. They've got a full outer shell. And now oxygen has a satisfied octet or a full outer shell at this point. So that means that this is a valid Lewis structure for water. Again, let's just draw it with the bonds. And maybe this time we'll put the hydrogens one on either side, and maybe the non-bonding pairs like this. And this is the Lewis structure for water. Now, you could have also drawn it kind of like I drew it here with, oops, sorry about that stray mark, with the oxygen bonded to the hydrogen, and then a lone pair on top and to the left. These are equivalent structures. They're completely the same. It does not make a difference. It's only when you get into molecular geometries that we'll have to be a little more careful how we draw things. But in terms of just getting the Lewis structures and what kind of bonds we have and where the lone pair or non-bonding pairs are, both of these structures are 100% fine. Okay, let's see if there are any questions. Yes, water is generally an easy one, but it's nice to see that the rules we have and the steps that we take work for making the Lewis structures. Okay, so that is water. Let's move on to our next one. So our next structure is oxygen gas, or O2. And again, we're going to follow the same rules here. I guess the easier thing about O2 is because it's just one atom bonded to another. There's no central atom, so you don't have to worry about trying to find the central atom for this case. Okay, let's add up our valence electrons. We've got 2 oxygens. Each oxygen has 6 valence electrons. So we're looking at 12 total valence electrons. And again, because there's no central atom, I'm just going to draw 2 oxygens next to each other. But I'm still going to do the same thing. I want to form a single bond first. So, oops, let me switch colors here. So I'm going to put 2 electrons here. And you can see, of course, I've got to use 12 valence electrons. I've only used 2, so for sure I'm going to have some non-bonding pairs. So let's go ahead and start putting in non-bonding pairs. Okay, so I've used 2. So this is 4, 6, 8, 10, 12. Just double check that. 2, 4, 6, 8, 10, 12. So that is 12 total valence electrons. So I can't add any more dots in because I only have 12. Now let's see if I have satisfied octets on both of these oxygens. Okay, so this oxygen is fine. It has 8 electrons around it, but obviously the oxygen on the right only has 6 electrons, so its octet is not satisfied, so this is not a valid Lewis structure. So I am actually just going to draw a line through this. I'm going to start completely over. If you have a pencil, of course, you can always erase and redraw things. That's totally fine. But sometimes I find it easier for me to just completely start over, and that way I don't get stuck. Okay, so here are my 2 electrons that I started with. And this is where I'm going to use my little hint here on the third rule that I haven't had to use before. And that is, if you try a Lewis structure and you see that you're not satisfying all octets, then try sharing more than one pair of electrons between atoms. So in this structure, I only shared one pair of electrons, or 2 electrons. So when I try again, I'm going to add a second pair of electrons. So instead of sharing 2 electrons, they are now sharing 4 electrons. And now I'm going to put the rest of my electrons in. So I've used 4, 6, 8, 10, 12. And let's just double check, make sure I've used 12, 2, 4, 6, 8, 10, 12. Okay, so I've used all my valence electrons. Let's see if I have satisfied octets here. This oxygen has 8, so again, it's fine. And this oxygen, you can see it now also has 8. So I have satisfied octets for both of the oxygen atoms. So now I do have a valid Lewis structure. And of course, I can draw this a little bit neater with bonds. And this is going to be a double bond. And I have 2 lone pairs, or 2 non-bonding pairs on each oxygen. And again, you don't have to draw the lone pairs like this. I could have easily put a lone pair right here. That's completely fine. Does not make a difference. You put your lone pairs where you want to put your lone pairs. Okay, that is oxygen. Let's make sure that we have no questions. All right, looks good. Doesn't look like there are any questions. Again, hopefully you're finding these easy and not a problem, so that we get comfortable before we go on to some more difficult ones. All right, CO2, carbon dioxide. We're going to start in the same place. We need to add up our valence electrons. So carbon gives me 4 valence electrons. Of course, oxygen, remember, you've got 2 of them here. So we have a multiplier of 2, and each oxygen gives me 6. So now I've got 4 plus 12, which is going to give me 16 valence electrons. Okay, so now what we need to do is we need to sketch out an arrangement. Again, carbon is written first, so I am going to assume it is the central atom. So let's put carbon here, and I'm just going to put an oxygen on either side. I really like things to be symmetrical, so that's generally how I sketch out my arrangement of atoms at first, but you can sketch it out however you would like. All right, so switching over to the green, let's put our electrons in. Let's make single bonds here. So 1 pair of electrons there, 1 pair of electrons here. Okay, so I've used 4 valence electrons, but of course I've got a total of 16 valence electrons. So let's just add in some more electrons. Okay, so 2, 4, 6, 8, 10, 12, 14, 16. Okay, just double checking. 2, 4, 6, 8, 10, 12, 14, 16. I have used all of my valence electrons. And now let's check and see if I've satisfied octets everywhere, because I don't think I have. Okay, this oxygen is fine. The oxygen on the right is also fine, but you can already see we've got a problem with the carbon here. So my central carbon, my central atom, only has 4 valence electrons. The octet is not satisfied. So this is not a valid Lewis structure. Again, I'm just going to, like I already did, I'm going to mark it out. I'm going to rewrite carbon and oxygen and try a different arrangement. Now, I've again run into the same situation that we ran into before, where carbon didn't have enough. So in this case, of course, I just made single bonds. They only shared 1 pair, so I'm going to make them share 2 pairs at this point. Okay, whoops, let me switch to the green. So we'll give this carbon and oxygen, they're going to share 2 pairs, and we'll keep this one at a single bond. Okay, so I have used 6 electrons, 6, 8, 10, 12, 14, 16. Okay, I've used 16 valence electrons. Let's see if everybody's satisfied. Okay, this oxygen here is fine. Other oxygen is fine. And again, carbon, we've only got 6. So we've made an improvement. We've gone from this first structure where carbon only had 4 valence electrons to this one where carbon now has 6. So we're on the right track. We made a good correction. We're just not quite there yet. Again, that one is not a valid Lewis structure. Let's try again. So we're going to go carbon, oxygen, oxygen. Since making one carbon-oxygen bond a double bond improved things, I am now going to make both carbon-oxygen bonds double bonds. Okay, so they're going to share 2 pairs. And also this carbon oxygen is going to share 2 pairs. So now I've used 2, 4, 6, 8. I have 16, 10, 12, 14, 16. Okay, this is looking better. I think this is it. All right, so oxygen on the left still has 8. Oxygen on the right has 8, and now you can see the carbon in the middle also has 8. So we have finally satisfied octets for all 3 atoms. This is our valid Lewis structure. And just like before, let's just rewrite this. Again, this is probably a Lewis structure you have seen before, but this is how it comes about. And then let's put in our lone pairs. And we'll make this one different. Why not? Again, it doesn't matter. Lone pairs don't have to be symmetrical. I just always tend to go symmetrical, but you don't have to. That's perfectly fine. So here is my valid Lewis structure for carbon dioxide. Again, before I go on, make sure there are no questions. And there are no questions. All right, great. Let's go on to our next molecule. Okay. So now we've done oxygen gas. Now we're going to do nitrogen gas. Okay, so N2. Again, with this one, just like we saw with O2, there's no central atom, so we don't have to worry about that. Let's get our total valence electrons. So we have 2 nitrogens. Each nitrogen gives us 5. So we have 10 total valence. And again, because there's no central atom, I'm just going to write the 2 nitrogens next to each other. Let's start putting electrons in. All right, as usual, I'm going to start with single bond. So there's my single bond. I've shared 2 electrons, 1 pair of electrons. So let's add in the next. That's 4, 6, 8, 10. You can already see that this is not going to work, but let's just show how it's not going to work. So the nitrogen on the left does have an octet that's satisfied, but the nitrogen on the right only has 4 electrons. Obviously, its octet is not satisfied, so I'm going to need to try again. All right, nitrogen, nitrogen. My hint says if sharing 1 pair leads to not satisfied octets, then share more. So instead of sharing 1 pair, we are going to share 2 pairs. So now I have used 4 electrons. 6, 8, 10. Again, you're probably seeing that this is not going to work. Okay, so this nitrogen actually has too many electrons. So you can see I have 2, 4, 6, 8, 10 electrons around this nitrogen. So it is over the limit. It can only have 8. And of course, the nitrogen on the right only has 4 electrons. So we've got one nitrogen with too many electrons and one nitrogen with not enough electrons. So why don't we try this first before we make it share more, because we've got one nitrogen with too many electrons. This time I'm going to attempt an erase. Let's pull this lone pair off. And let's give it to this nitrogen on the right, and let's see if that fixes things. So now the nitrogen on the left has 2, 4, 6, 8 electrons, so it's fine. It's got a satisfied octet, and we haven't gone over. But you can see the nitrogen on the right, while it is improved, it now has 6 electrons. It's still not quite there yet. So we've shared 2 electrons. That hasn't worked. We've shared 4 electrons. That's not working. Let's make it share 6 electrons, or 3 pairs of electrons. Oh, let me draw my red line through that. I don't want anybody to think that that is the valid Lewis structure. Okay, so again, my nitrogens are bonded, and now I'm going to put 3 pairs. Okay, that's a lot of electrons in between there. So I have used 6 electrons. And now I have used 8. And there is 10. Okay, let's check octets. Okay, so this nitrogen, you can see 2, 4, 6, 8, 10. Again, it's got too many valence electrons. And look at this nitrogen here on the right. It doesn't have enough. So this is what I mean by guess and test. You're constantly counting and checking and moving things around. So just like we did with our previous attempt, even though it turned out wrong, let's take a pair of electrons here. Let's move it to the nitrogen that doesn't have enough. Now, when you move pairs of electrons around like this, always double check and make sure that you still have the correct number of valence electrons. So I should have 10. So 2, 4, 6, 8, 10. It's really easy when you're erasing and drawing things in to either drop a pair of electrons or inadvertently add a pair of electrons in. So it's always nice to double check that. And you can see that now both the nitrogen on the left and the right do have satisfied octets, because there are 6 in between, and each adds 1 lone pair or non-bonding pair, and that gives both nitrogens 8. So now we finally have our valid Lewis structure, and I'll draw it under here a little bit neater. So we have nitrogen has a triple bond to nitrogen, and each of them has 1 lone pair. So hopefully, especially in this structure, you can more see the process of the guess and test and moving electrons around. And, we tried a single bond and we tried a double bond kind of twice. We moved some lone pairs around and that still didn't work. And then we went to the triple bond. And even then we had to move some electrons around. So never feel like when you do Lewis structures, you have to get the correct Lewis structure right away. Especially at first, before you're used to this, there's going to be a lot of either doing what I do and you mark through and you start over, or if you're using a pencil, there's going to be a lot of erasing and trying again. That doesn't mean you don't understand Lewis structures. It just means you're learning. Now, before we go on, I just want to make sure that, yes, good, there are no questions and everybody is still with me. Let's go on to our next structure. Okay, we're doing a lot of diatomics, aren't we? So this is chlorine, Cl2. Same deal. Let's add up our valence electrons. So we have 2. Each chlorine gives me 7. That gives me a total of 14 valence electrons. All right, again, the nice thing about this is we don't have to worry about a central atom because it's just a chlorine bonded to a chlorine. And let's put some pairs in. All right, so just like usual, I'm going to start with single bond. All right, so that's 2. I've got 12 more electrons to do. So 2, 4, 6, 8, 10, 12, 14. Okay, so I have used all of my valence electrons. And let's see if I've satisfied octets. So the one on the left is good, and the one on the right is good too. So this one was actually a really easy one. It was a single bond, and I just filled in the rest of the electrons, and everybody's octet is satisfied. All right, so this is going to look like chlorine with a single bond to chlorine, and let me get all of these non-bonding pairs in. So sometimes a structure might at first glance seem like, oh no, this is going to be tough, and it ends up being really easy. But of course you have the flip side where sometimes you think, oh, this one's going to be really easy, and it ends up being pretty tough. Okay, so that's chlorine, just no questions. Okay, we're good. Let's go on to carbon monoxide, or CO. All right, let's add up our valence electrons. Carbon gives me 4, oxygen gives me 6, so I have 10 valence electrons to work with. Again, nice thing is we don't have a central atom, so I just have carbon bonded to oxygen. Let's start with our single bond, just like usual. So hopefully you can also see just the pattern here, the repetition. We're kind of doing the same thing over and over and over again. Okay, there's our single bond. So that's 2, let's see, 4, 6, 8, 10. You notice it's my habit to always fill in the octet on the left. Maybe you like to fill in the octet on the right. You can do it either way. It really doesn't make a difference. And of course, my carbon does have a full octet, but my poor oxygen has only got 4 electrons. So nope, that one did not work. Let's try again. Now I'm going to make them share 4 electrons. So that's 4. Oh, I didn't change the color. Sorry about that. Okay, so that's 2, 4, 6, 8, 10. And I'm guessing you guys already see I have problems with this one. So my oxygen still only has 4 electrons, but now my carbon has 10 electrons. So let's erase a lone pair and put this over here next to oxygen. Okay, so again, we've kind of improved things. Our carbon now only has 8 valence electrons. Its octet is satisfied. We haven't tried to cram 10 electrons in there, but my oxygen only has 6, so I'm close, but I'm still not there yet. Let's try again. Carbon, oxygen. This time I'm going to try a triple bond. I'm going to put 3 pairs of electrons here, so that's 2, 4, 6, 8, 10. This is looking promising. Okay, so that carbon does have 8 electrons. This oxygen also has 8, so I have satisfied octets for both carbon and oxygen. So I have found my valid Lewis structure. And let's just write it out a little bit neater right below it. So I have carbon with a triple bond to oxygen, a lone pair here, and a lone pair here. Okay, that is carbon monoxide. So you can see hopefully that we're starting to troubleshoot a little bit faster and a little more comfortably, which is exactly where we want to be. All right, let's move on to our next structure. Okay. Oops. So we've got carbon tetrachloride, or CCl4. Let's add up our valence electrons. So carbon gives me 4. Plus I've got 4 chlorines. That's 7. So 4 times 7 is 28, plus another 4 is 32 valence electrons. We're certainly not running out of valence electrons with this structure, are we? Now, I do need a central atom here, so because carbon was written first, I'm going to put carbon in the middle, and I'm going to put my chlorines all on the outside. So we have carbon, chlorine, 3, 4 chlorines all around. Again, I'm going to start with my single bonds. So each carbon chlorine is first going to share one pair of electrons. So I have used 8 electrons and I've got to get to 32. So I'm going to start putting electrons in. So this is 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. Those are all my valence electrons. Okay, so I have used 32 valence electrons. Let's check octets. Well, I already know that carbon is good because it has formed 4 bonds. But let's check my chlorines. Okay, so yes, that chlorine has 8. This one also has 8. So does this one, and my last one also has 8. So this structure, maybe at first you thought, yeesh, especially with 32 valence electrons, this might be a bit of a bear, but actually it turned out to be pretty easy because we just did single bonds and then filled in a bunch of non-bonding pairs. Okay, so let's draw this a little more neatly. So we have carbon in the middle. It's got a single bond to each of these chlorine atoms and lone pairs all around. So it's going to take me just a second to draw in all of these lone pairs because there are a lot of them. And one more. There we go. All right, so this is the Lewis structure for carbon tetrachloride. Okay, no questions? Let's move along. All right, SO2, sulfur dioxide. Same thing. All right, so sulfur, you can see, is right underneath oxygen. It gives 6 valence electrons. Plus, I have, again, 2 oxygens here. They give 6. So I have 12 plus 6. I've got 18 valence electrons. All right. So now I'm going to sketch out my arrangement. Again, because sulfur is written first, I'm going to put that in the center. So sulfur, and I'm going to put oxygens on either side. Let's start putting in electrons. All right, so as usual, single bonds first. I've used 4 electrons, 2, 4, 6, 8, 10, 12, 14, 16. I've got 1 more pair to use, so I'm going to put one here on sulfur. Okay, I have used 18 valence electrons. Let's check octets. All right, this oxygen is fine. I have some problems with this sulfur, and this oxygen is also fine. So we have used all 18 valence electrons with single bonds, and we're not getting octets satisfied, so let's make them share more. Okay, so let me make sure that one is not valid. Let's start over with our sulfur and our oxygen and our oxygen. And I'm going to make the sulfur-oxygen bond on the right a double bond. So they are going to share 4 valence electrons, but I'm going to keep the one on the left a single. So now I have used 6 electrons. I'm actually going to go ahead and give sulfur a lone pair so that it already has 8. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so I have used 18 valence electrons. Let's check octets. All right, so I already know that I gave sulfur 8. And this oxygen also has 8. And this oxygen also has 8 valence electrons. So we have satisfied everybody's octet here. All right, so let's rewrite this. Sulfur in the middle, we have a double bond to the oxygen on the right with 2 lone pairs, and a single bond, the oxygen on the left with 3 lone pairs. And let's not forget our lone pair on sulfur. Now, this brings up a question with this Lewis structure. You'd say, well, okay, I just decided to make the double bond on the right-hand side between the sulfur and the right-hand oxygen, but couldn't you have made the double bond with the sulfur and the oxygen on the left? And the answer is yes, absolutely, you could have. So I can also draw this Lewis structure. Let me put brackets around this, with the single bond to the right and the double bond to the left. And I don't want to forget my lone pairs. Now, when you do this, make sure that you keep the lone pairs the same. So because I moved my single bond to the right-hand side, that means I now need 3 lone pairs on that oxygen on the right. And the one on the left just gets 2. And we put brackets around this just so it's easier to see what the structure are. But these structures are called resonance structures. So sulfur dioxide has 2 different ways that we can draw the Lewis structure. You can either have the double bond on the right and the single bond on the left, or the double bond on the left and the single bond on the right. They are both valid Lewis structures. And very often you will see both of these Lewis structures drawn. So that is resonance. That's a really quick view of resonance, but that is resonance. So I have a question about formal charges, but actually that is beyond the scope of at least this live stream. I just want to get Lewis structures down, but we can definitely do problems where we deal with formal charges later. But that's a very good question. That's a little bit more advanced than I want to get right now. Resonance is about our max here. Okay, so that is sulfur dioxide. Let's go to our next Lewis structure. Here we've got the ammonium ion. So this is a polyatomic ion. And for the first time in at least this live stream, we are going to have to deal with charges here. And how do we do that with electrons? All right, so we're going to dive right into it and we're going to see how to deal with that charge. So we've got a nitrogen atom that gives us 5 valence electrons. We have 4 hydrogens. They each give us 1. And now we need to deal with this charge here. So when you have a positive charge, it means you have lost a valence electron. So in this case, I'm going to add a -1. You could also just subtract 1. This kind of depends on how you think about it, what makes the most sense to you. So you can either write it like this, or you can say 5 plus 4 times 1, just minus 1. They're both going to give you the same answer. So we have 9, so we're going to have a total of 8 valence electrons. Now, you can have structures that have an odd number of valence electrons. Those are called radicals. We are actually not going to deal with that in this live stream. That's another thing that's just going to be beyond the scope of what we're going to be able to cover today. But if you want, we can always do another live stream where we talk about radicals and we see their structure. Okay, but we have our total valence electrons. Again, I'm going to put nitrogen as my central atom because it's written first. So we have nitrogen and we have 4 hydrogen atoms around here. All right. Let's start putting pairs in. So you probably already see where this is going. Those are my 8 valence electrons. I have no more. So I'm going to check octets. All right. So nitrogen is good. It's got 8. Now remember, hydrogen only needs 2 valence electrons to have a full outer shell. So that hydrogen does have a full outer shell. And you can see that actually all 4 of my hydrogens do have a full outer shell. So this is a valid Lewis structure. So let's draw it a little more neatly, a little more clearly. So we're going to have nitrogen with a single bond to each of the hydrogens. And we also want to specify that this has a formal charge, so we will use brackets. And I'm just going to put the positive charge on the outside. So this is the Lewis structure for the ammonium polyatomic ion. Again, before I go on, I just want to make sure that there are no questions. And there are no questions. So let's do a different polyatomic ion. So here we have cyanide. So in the ammonium polyatomic ion, we dealt with a positive charge. So now let's deal with a negative charge. Okay, so adding up valence electrons, carbon, of course, gives me 4 valence electrons, and nitrogen gives me 5, and now I have to deal with this -1 charge. So a positive charge means, of course, that you have lost an electron. A negative charge means you have gained an electron. So I am going to add 1 here. And of course, that gives me 10 valence electrons, which we have seen a couple times, so I think you know how this is going to go. We have carbon bonded to nitrogen. And just like usual, let's make them share 1 pair of electrons. So that's 2, 4, 6, 8, 10. And, you know, you guys knew this wasn't going to work. So carbon's fine, but nitrogen only has 4. So in this case, let's erase that one. We're going to be a little sneaky now. And I'm going to put that pair in here. Now, again, when you start erasing and rewriting pairs, make sure that you still have used the correct number of valence electrons. So I'm just going to make sure 2, 4, 6, 8, 10, that I still just have 10 valence electrons. Again, it's really easy to lose a pair or add a pair in. Okay, so with the double bond, we've definitely improved things. The carbon still has 8 valence electrons, so it hasn't lost anything. The nitrogen now has 6 instead of 4, so that is good, but we're not quite there yet. So again, you guys know where this is going. I'm going to put a pair in here, which means I have to erase out of here. Again, let's double check and just make sure we have 10. 2, 4, 6, 8, 10. I would say drawing in another pair before you erase a pair is probably going to lead to extra pairs being thrown in, so just be careful about that. And I have used my 10 valence electrons. I have satisfied octets for both carbon and nitrogen. So I'm going to rewrite this. Carbon and nitrogen have a triple bond, and they each have a lone pair. Now, because this has a formal charge, I'm going to put brackets around it, and I'm going to put that negative charge there on the outside. Okay, great. Let's go on. I think we can fit in at least one more. Yeah, and this one is actually a really good one to do. So this is nitrate, again, another polyatomic ion, so we're going to have to deal with a charge here. So nitrogen gives me 5 electrons. We have 3 oxygens. They give me 6. Again, my negative charge means that I have gained an electron, so I'm going to add 1 there. So I've got 24 valence electrons. All right, I got a lot of valence electrons to deal with. Assuming nitrogen as my central atom. So I have nitrogen, oxygen, oxygen. As usual, I'm going to start with single bonds. So single bonds here. That is 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. These electrons over here got a little messy, didn't they? Okay, it's 24 electrons. Let's check octets. Oxygen is good. Oxygen is good. Oxygen is good. Oh, we were close, weren't we? Nitrogen is no good. Nitrogen only has 6. You kind of feel like as you're drawing these lone pairs in and you get to that last one, you think, oh, I think I've got it. But in this case, we didn't have it. But nitrogen's only missing 1 lone pair. So again, when we don't have octets satisfied, let's make them share more. So I am going to erase this lone pair. I'm going to make a double bond here. Okay, again, because we did erasing and rewriting, let's make sure that we have 24 valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Yes, okay, so we should be good. We've got our valence electrons. And you can see that we have nitrogen has one double bond to an oxygen and a single bond to the other two. So let's write this out a little bit neater. So we have nitrogen. It's got a double bond to the oxygen on the right, and this has two lone pairs, and a single bond to these other two oxygens. So I think you can guess where I'm going to go with this. But let me first finish drawing this out. Let me put my brackets in. It's got the -1 charge. We did not have to form that double bond with the oxygen on the right. There's nothing special about the oxygen on the right. We could have done the double bond with the oxygen that was underneath. So this means we have resonance structures. So let's make the double bond with the oxygen that was below the nitrogen. Again, let's put in lone pairs. And when you do these resonance structures, just make sure that you're keeping track of how many lone pairs go around each oxygen. So remember, with your double bond, that oxygen only has 2 lone pairs. That's 8 total valence electrons. Let's do my brackets, give my negative charge. But of course, in this case, we actually have a third resonance structure. I think I'm going to have to draw it below, because the double bond could be for the oxygen on the right, it could be for the oxygen below, or it could be for the oxygen on the left. So we also have a third resonance structure where I put my double bond on the left. And let me get my valence electrons in. Almost. And let me get my brackets and my negative charge. So this Lewis structure has 3 resonance structures, or 3 valid Lewis structures. A lot of times you'll see resonance will maybe just be between 2 different structures, but know that you can have more than one resonance. In this case, we had 3 different resonance structures. And I see that we are actually already at 8 o'clock. So let me know what else you want to see with Lewis structures. We weren't able to go back and put in, do our VSEPR and do molecular geometries, or do dipole moments and overall dipoles. So if that is something that you guys want to see, please let me know. You can email me at Karin@ChemHelpASAP, and we can certainly do a live stream on that. Well, thank you very much for watching.